Okay. Um, so a change of direction because it occurred to me when looking at the calendar that we don't have a whole lot of semester left. Thank goodness. Yeah. Well, so we have 4, 11, 18, and then partial week. And then 1 week after Thanksgiving, and that's it. And I realized, wait a minute, I still have stuff to cover. So, um, and at least some of which is needed towards the ending homework problems. So, plus, at the very end of a semester, during finals week, I schedule with each of you individually, so like a oral final, and I want to be able to put something on it. And that would not be okay. I would not have you writing MATLAB code on the board. So there may be some slightly MATLAB related questions, but really it's more about just the properties of the methods and things like that. I'll have more to say about that when it gets closer to that time. Because we got to the end of chapter 3 on spectral methods, although I just realized there's a little bit of that I didn't cover, but I'll deal with that later. And then there's still chapter 4, and if time permits, chapter 5 in the notes. And with Carly not here today, I figure I'll just plow ahead through the notes, and we'll see how far we get. If I get to a good stopping point and there's homework questions, we can take those, but also we can use Wednesday to return to homework. And hopefully get at least those first 3 problems from that finite difference assignment squared away. And then there'll still be some time for the next 2 problems in spectral methods, and then there's a multi-grid problem or 2 at the end. And I haven't even talked about multi-grid at all. And that's in this chapter. So I might want to get at least that far. Okay, so So for much of a semester, we're dealing with time-independent PDEs. And when I say elliptic PDEs, well, who remembers from PDE class, there's 3 different ways of classifying second-order PDEs. Elliptic is one of them. That's another way of classifying it's independent of that, but there's...
Hyperbolic.
What? Sorry, what?
No.
Yes, go.
Hyperbolic.
And what? Yes, and what's the other one?
That's not coming to me.
Okay, all right. They deal with conic sections. Parabolic, yeah, is the other one. So, and elliptic is really, so that's like Poisson's equation. So that's really going to be the focus of this chapter. Whereas hyperbolic is a wave equation. Parabolic is a heat equation. But when you have an elliptic PDE like this one, we've already seen that when you discretize it, that PDE becomes a system of linear equations. So this form A equals F. We're already seeing that in the homework. Now, so far, all I've talked about is how we go about setting up that system from finite difference formulas, center difference and all that. As we're dealing with the homework, how the system is set up, and then once it is set up, in MATLAB, you're just doing backslash and voila, there's your solution. And it's a total black box to you all. So in this chapter, we're getting under the hood. We're getting into that black box and looking at the different numerical methods that can be used for solving this system. And although MATLAB has a backslash, okay. That you can always use, it's not the only thing that MATLAB provides. Now, when you use backslash in MATLAB on a system of equations like this one, it does Gaussian elimination, along with partial pivoting. Actually, once elimination is done, what happens after that? What are the remaining steps? Because Gaussian elimination, all that does is reduce the matrix A to an upper triangular form. I mean, there's something that needs to happen after that. Yeah, substitution. What kind of substitution? What do we call that? But it's upper triangular. Yeah, it's back substitution. Okay. Which is the most general method of solving a system of linear equations. But it's not necessarily the best one to use in all cases. There are iterative methods. Some of which are covered in 610, some of which are covered like in the 560, 561 sequence. So I'll be spending some time talking about those. And these are, that's for a case where A is sparse, which is what we have in most cases when dealing with PDEs. So certainly those methods are of interest. Okay. And we'll have more to say about system setup also, because so far we've done the one-dimensional PDE, so like minus UXX equals F. Well, how does that carry over to a two-dimensional or three-dimensional problem? So there's some details there that need to be worked out. So in fact, that's actually the first thing I'll talk about. Okay. So okay. All right. So I have minus uxx plus uyy equal to f. And we'll put this on a square. So x and y ranging from -1 to 1. And we'll also assume that u is 0 on, okay, I'm going to call this domain omega, the square. So this is the boundary of omega. So same boundary conditions we usually have. But now, whereas in 1D, u being 0 in the boundary just meant u is equal to 0 at x equals 0 and x equals 1, 2 points. But now, u is equal to 0 on the entire boundary of a square. Okay. Right. So we know how to handle this in the one-dimensional case. You've done it in the homework. So once you've done that, how do you handle for the 2D case? minus uxx equals f on the interval, say, well, actually I'll be consistent, minus 1 to 1. And then you have minus 1 equals 0, you have 1 equals 0. And what's happening in that case is you set up a system of equations and you solve this system. I'll call it K1D times U is equal to F. And K in the 1D case, is that, yeah, not sure why I called it K, but whatever. So this is a matrix that's familiar to you by now. Oh wait, positive 2. Okay. But that symmetric tridiagonal matrix. Okay. And H is equal to, in this case, 2. The length of the interval is 2 over n plus 1, the number of grid points. We're accustomed to 1 over n plus 1, but that's for the interval 0 to 1. Now we're in a larger interval. Okay. So, ideally we'd like to be able to use this to be able to handle the two-dimensional case. Now, I'm going to give you an idea of what the matrix looks like. So, like basically the hard way of getting it, and then I'll be able to show you that there is actually an easy way in MATLAB to get the right matrix in the 2D case. Now, in 1D, look at the right-hand side F. Relatively straightforward. It says the values of your right-hand side through PDE at your grid points. They're just in your whatever interval you have, like from minus 1 to 1 in this case. Now, so what do we do in 2D? Because we still want a system of equations like this, where we have a right-hand side. But if you're in 2 dimensions, you tend to think of F, like if you're going to represent F in 2 dimensions, you'd think of it as what? One step up from a vector.
Matrix.
Yeah, it'd be a matrix. But we still need a vector, so how do we reconcile that? And the key is in how you have to assign an ordering to all the points in your domain. So if we're in the other domain 1, okay, draw a very bad square. Now, you know what your solution is on the boundary, 0. Wow, that is a very off-kilter square. So it's in the interior, where you'll have grid points. Now, it's natural to label these grid points as using 2 indices. like for row and column. And but we also have to be able to label these grid points using just one index. It starts with this would be point number 1, and maybe this would be point number 2, and so forth. Okay. Now, the thing is, so for example, I could label this as point 1, 1, naturally as the starting point. And then I could label this as point 1, 2, or 2, 1. So that's what can cause confusion, is that there's ambiguity. There's more than one way to go about it. Now, MATLAB has a sort of natural conventional way of ordering points. So that's what I'm going to try to go with here. Okay. All right. So if we think of these, one is kind of like being row and column indices in a matrix. Because columns go from left to right, and x is going left to right, it makes sense to associate x with a column index. So I'll call this point 1, 2, 1, 3, and so on. And then everything in the first row in y. And then go to the next row in y, 2, 1, 2, 2, and so forth. So what we have here is so for 2D, I could order my points in my vector as follows: f of x1, y1, and then I'll go to x1, y2. So notice only the y value is changing at first. It's always x1 until we get to f x1, y, m. Now, I've been using capital N to refer to a number of x values, and I'll continue to do so. I'll use capital M to refer to how many y coordinates we have, because they don't have to be the same. So once I've gone through everything for x1, then I switch to x2 and go back to y1. And keep going. And we just keep cycle going like this until we get all the way to the bottom. X, N, Y, N. Okay. So that's the natural way in which, or it's one way in which the points can be ordered. But it's a way that happens to work well with MATLAB's conventions. Okay. Now, so that's what your right-hand side F would look like. But what about the matrix A? Because now, in one dimension, we are approximating minus UXX. We use a center difference. Well, here we'll also use a center difference, but it has to be done in X and Y. So Laplacian at a point Uij is going to involve, first we have points to the left and right, just like in one dimension. So for the center difference in X. So this would be point Uij plus 1 and Uij minus 1. Notice only the second index is changing because we're only varying X. So this part covers UXX.
Wait, we're only
Varying the second index.
Right.
Column index is for X.
Yeah, okay.
Okay,
Yeah.
yeah, all right. And then we include points right above, right below for UYY. Also center difference, this direction. So this would be UI plus 1J, UI minus 1J. So this is called the 5-point Laplacian. So Laplacian at point xi, yj depends on points in north, south, east, and west. Okay. Now, how's that going to be reflected in the matrix? Is it going to look something like this that we have from a 1D case? And the answer is yes and no. Because notice here, if you're ordering points in this manner, points with neighboring y values are next to each other. But points that have the same y and different x's far apart. They're n apart. So what does that do to the matrix? I'm actually going to write two matrices. One for UXX and one for UYY. And we can add them. So I can do YY first because that's simple. So the way UYY looks is looks much like the 1D case because, as I mentioned, points of consecutive y values, same x, are next to each other in the ordering. So we would have something like this, the 1D matrix. Okay, this is minus UYY. And this covers points with corresponding to x1. And then we repeat. Same kind of matrix. There's a 1 over h squared out front. And this corresponds to x2. And so forth. So, if I write this in block form, you have K1D, the 1D Laplacian, going down the diagonal. Everything else 0.
What is K1D and then K?
K1D again.
Oh, okay.
Same matrix. So it's like a tiling away. That you have these tiles of K1D going down a diagonal. Okay. What about minus UXX? That's going to be a bit stranger. There's still 1 over h squared up front. But now, like you're going to have a 2 on your diagonal, like before, and then that's going to reference points at the next x coordinate over, which is n points away. So you're going to have nothing, zeros, and then there'll be a 1. Oh, sorry, a -1 way over here. And similarly, if I go to the next row, there'll be a 2. So 2's down the diagonal. And then -1's n points away. Okay, I think I need to make this bigger. Down here, so for the next block, I'm going to have 2's down the diagonal, -1's, n points to the right, and -1's again over here, n points to the left. So, and this pattern continues. So if I write this also in block form, I can think of it this way. This smaller block here is the identity matrix times 2. So I have 2 odd here. Next to it, minus identity. And then next row, next block row. That keeps going. So it's another kind of tiling. So here I have tiles themselves have the structure of K1D. But what goes in the tiles is identity. Here, the tiles themselves form identity. What goes in each tile is K1D. So it's the opposite. So then I would add these two together for the Laplacian. So I'd end up actually with 4's on the diagonal, and these minus 1's all over the place. But there's actually a easy way to describe this, what's going on here in both cases. Okay. So, okay. So I can describe this matrix as identity Chronica Product. That's what the funny circle with the times in it is. Chronica Product K1D. Which in MATLAB, they have a function for it, just cron, K-R-O-N. That carries it out for you.
Wasn't that in 516 Chronica? Is that
Chronica Delta.
Yes.
Yeah, Chronica had a lot of things named after it.
Okay.
This is the opposite. It'd be cron. It would be K1D Chronica Product identity. So this operation is not commutative. Okay. I guess I should describe what Chronica Product actually is. Yeah. So in general, I have A is
Chronicus K-R-O in
E-C-K-E-R.
oh yeah. Sorry, I haven't written it out yet. Okay, so let me write that out here. Chronica Product. That's MATLAB's cron. Okay. So you assume that A is m by n, and B is p by q. Okay, so there's no compatibility required of sizes, unlike regular matrix multiplication. Okay. So A Chronica Product B is going to be m times p, so the row dimensions get multiplied, times by n times q, so the column dimensions also get multiplied. And where it can describe the product is, here's a good way to look at it. You basically have, because the size of A is m by n, it gives you a m by n tiling of B. So it's like you're arranging B, filling in an m by n pattern. Okay. So the size of A indicates how many tiles you have in each dimension. But I should have mentioned that I left a little space in there intentionally. Each tile, the ij tile, you multiply by the corresponding entry of A. So I have A11 B, A12 B, A1 N B, and then A21, A22, A2N, and then A M1, A M2, A M N. So tile B, then multiply each tile by an entry of A. That's a Chronica Product.
And where does A come? That's the entry of.
Yeah, so all of these are entries of A.
Okay.
And each entry is multiplying the whole of B. That's why it's such a large matrix. Okay. Okay. So now let's keep that description in mind when looking at what I did over here. Here, the second matrix is one that fills the tiles, K1D. K1D is everywhere. But what do they get multiplied by? The elements of identity. That's why only the diagonal blocks actually have something, because only the diagonal of identity has anything non-zero in it. The rest of the blocks, you're taking K1D and multiplying it by 0. Same thing here. You fill every tile with identity, then you multiply it by 2's and minus 1's, the entries of K1D. So that's why each one of these is a Chronica Product, just in a different order. So the nice thing is, if you want to do a discretization of Poisson's equation in 2D, so so I should say minus Laplacians, because we're sticking minus in front. So in 1D, you just have K1D by itself. In 2D, you have K1D Chronica Product identity plus identity Chronica Product K1D. And that's your Laplacian. And finally, in 3D, you have K1D Chronica Product I plus identity Chronica K1D, Chronica I, plus I, Chronica K1D. So
The K1D doesn't have anything to do with Chronica. They just are both Ks.
Yeah,
they would start
I think I just got that out of whatever notes I had. So
with- okay.
yeah.
Just,
It's a 2D. Sorry. K1D is the center difference. It's minus UXX. So here we have all possible Chronica products involving two identity matrices and a K1D. It gives you three possible orderings. Since Chronica product is not commutative, but it is associative, just like regular matrix multiplication. Okay. So MATLAB setup on the matrix side is really easy. You just make your 1D matrix and then do a whole bunch of however many Chronica products you need, based on however many dimensions you have. So in 2D, if you're using n points in both x and y, this would be an n squared by n squared matrix. This would be n cubed by n cubed. So you definitely want to be using sparse matrices, or you'll run out of memory really quickly. Okay. All right. Now, that's the matrix setup. But what about the right side, the F? Because I mentioned how, like in F, you have, like in 2D, it's natural to think of f of x, y as being arranged in a matrix, but we still need a vector. So what's the easiest way, especially in MATLAB, to get that? And thankfully, it is easy. At least MATLAB gives you the commands that makes it easy. So So what you can do is, let's suppose you make a vector of x values, x1, x2, xn. And I'm going to assume that you have a MATLAB function. You have some formula for f of xy. So something you could easily code up as a MATLAB function. And you can evaluate f of xy at any xy you need. Okay. So you form a vector of x's and also a vector of y's, y values. And the number of points don't have to be the same. Then, here's what you can do. So let's say you make these vectors in MATLAB. Then you can use this handy function called mesh grid. So you pass your x and y vectors as arguments to mesh grid. And what mesh grid outputs are matrices that have the correct x coordinates and y coordinates to evaluate a function on a 2D domain. So here's what x2 looks like. x2 is going to have x1, 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 x2 down the second column, and so on. So it's going to have, so it's going to be m by n. Okay. Which makes sense because x, we think of x as going from left to right. So as we go from left to right, each column is a new x value. And then y2 will cover the y coordinates. So first row would be all y1s, y2s, and ym. Okay, so again, for both matrices are m by n. So if you put the two together, you have all possible ordered pairs of x's and y's in your domain. So then I could plug in these into my, suppose I have little f as a function handle in MATLAB. I can just plug those in. I need to make sure that my function works on vector or matrix arguments, by using dot multiplies and stuff wherever you need them. So this is now an m by n matrix of function values. At all the ordered pairs in the domain. Now, we have a matrix, but we still need a vector for our system linear equations. Also easy to get. All that's left is to use MATLAB's reshape function. And we want a column vector. Now, what reshape does is it takes whatever vector or matrix you give it, and it changes the dimensions. The total number of elements cannot change. You're taking the same data, you're just viewing it differently. So it's often used to reshape a vector into a matrix, or vice versa. So in this case, I want to reshape this matrix into a column vector. So you do num_L. Num_L is short for number of elements. This is the number of rows you want, followed by the number of columns you want, which is 1, because it's a column vector. And that's it. You have your right-hand side. Now, very important quasi-computer sciencey point. How does reshape actually do its job? How does it form this matrix into a column vector? But keep in mind that f has this layout. F of x1, y1, f of x2, y1, f of xn, y1. And then f of x1, y2, x2, y2, f of xn, y2, all the way down to f of x1, ym, x2, ym, xn, ym. So there are different ways in which we could arrange all of those values into a column vector that has m times n elements. Like if I were to iterate over all these numbers in some natural ordering to stuff these into a column vector, what are two different orderings I could use? Because technically I could put those, if I have a matrix of mn elements and a vector of mn elements, I could place those in there in many different possible ways. But some are more natural than others. I like to go through these elements in an orderly fashion. So what would be one? Just think of one way I could iterate over all these.
Like the rows and then the columns? Or
Okay. Well, okay. Let's go with that. You said the rows and then the columns. So specifically, what would I pick up? I mean, obviously, I'd start here.
Right.
So what would I pick next?
If you're doing a row.
Like which element? Where would I go next? Just pick.
Just go down.
Yeah. Okay. So I pick that one, and then what?
To go down again.
Okay. And then
Go back up to the top to the next column.
I feel like Chinese takeout. And then. Yeah. And then yeah. So I go through a first column, second column. Yeah. So that's one natural ordering. So that's called column major ordering. So consecutive elements are stored. So elements within a column are stored consecutively. All right, that's one way. What's another way?
Row.
Yeah. So I go through the row. That's called row major ordering.
Diagonals as well, or no?
It's not very natural though. It's kind of cumbersome. But yeah, there are cases where it's used, helpful. But yeah, those are the two essential orderings conventions you follow: row major or column major. Now, different programming languages use different conventions in how they lay out two-dimensional arrays. So, Fortran, the first one, column major ordering. C and C++, row major. Now, MATLAB is built on Fortran code at its lowest level. So, reshape uses column major ordering. So, the way it will build this vector f from the matrix capital F, it'll first put these first column entries in the vector. So, it'll go like that. Okay, so first column, second column, third column, and in order within that column. Which, by the way, is how I ordered the points when I wrote out the vector several boards ago. And I did it deliberately to conform to this. So that's what reshape is doing. So MATLAB's functions are built around this way of ordering points. You can't order them the other way, but then MATLAB's functions are like, so you better like do some transposings or something. But at least this way, setting up your system equations for 2D Poissons or 3D Poissons is all fairly straightforward. That you make your x's and y's, mesh grid, evaluate, reshape, done, and your system is set up. So that's your right-hand side. In matrix, you make your 1D centered difference, Chronica Product, add them together, matrix is done. So you could write a 2D Poisson solver in just a few lines. Okay. Let's see. All right. So any questions about all that? Okay, some of the later problems in the homework we'll deal with 2D. I think like the ones toward the end. Let's see. Oh yeah, because problems 4 and 5 in the homework are still 1D. There's only one 2D problem in the entire homework. Wow. The very last one, number 7. I'm glad I spent so much time on this then. Okay. Okay. Now, sadly, none of this is in the notes, really, or hardly any of it. Yeah, these notes need to be flushed out a bit more. But okay. Now, so there's one interesting thing about the two-dimensional matrix that's quite interesting in terms of how you go about solving Ax equals B, because once you have it, then yeah, you can use whatever methods MATLAB offers for solving the system, like Gaussian elimination or iterative methods, etc. But sometimes there's a little rearranging of equations and unknowns that can be carried out to make the system easier to solve or more efficient to solve. Okay. Now, I'm going to assume that the number of points in the x and y directions are equal, and also that n is odd. Now, your matrix A has this layout. So there's 4s all the way down the diagonal. Right, there's a 1 over h squared out front. Can't forget that. And then I'm going to segment this. Okay. So we have -1s immediately to the left and right of 4s, or segmented with respect to y. And then over here we have these -1s. Okay. And same thing down here. Okay. Oh, and these people also. Okay. Above and below. Okay. Now, this matrix is pretty sparse, which is nice, but there's something we can do to break the system down, like actually decouple it in a way. So this matrix uses what is called lexicographic ordering. Of all the grid points. So points are numbered consecutively, like all the points for a specific x value first. Then we go to the next x value and number those consecutively. So there's other ways to order the points, especially in higher dimension. So instead, we could use what is called red-black ordering. Now, if you're on a grid, these points, what?
It's like checkers.
That's exactly it. Yes, we treat it like a checkerboard. Now, it's too bad I don't have colored chalk here. I'm not sure how black chalk would work anyway, but I'll use X's and O's. So, alternating points are not adjacent to each other based on their compass directions are red. So red corresponds to the X's, and so like for instance, I could number the first point, label the first point as red, and then points that are adjacent to it along compass directions, so not kitty corner. So points left, right, above, and below are black. So I make sure that no two adjacent points have the same color. So it just gives you a checkerboard pattern. Okay. So what I can do is I can in columns and group the red and the black points together. Well, the nice thing about the Laplacian 5-point stencil is, if I fill in a few more of these, now Laplacian 5-point stencil, you're evaluating Laplacian at a certain point, and you're using the points that are north, south, east, and west. So if I'm evaluating Laplacian at a red point, it's the only red point. So Laplacian at a red point involves only black, and vice versa. So the matrix has a nice structure because the 4s correspond to one color, and the -1s correspond to the opposite color. Or I should say, half the 4s are all red, and then the -1s that go with those are all black, and vice versa. So the matrix looks like this. 4 segments. So here are all the 4s for the red points, and here are the 4s for the black points. These columns correspond to red unknowns. These correspond to black unknowns.
Can you label that? Which ones are red, which ones are black?
So these are red unknowns columns.
Red
These are black unknowns columns. So the -1s that are associated with these red points are all over here. So there's some arrangement of -1s, and there's more than one diagonal of them. I don't remember the exact arrangement, but the point is, and the same thing over here, the -1s associated with these 4s all belong to red points. So we're going to have various diagonals -1s in here also. But these blocks of size n/2 by n/2, roughly, they're diagonal.
If the columns correspond to the red and black points, do the rows correspond to anything?
Okay, columns correspond to unknowns. Rows correspond to equations. So you can say that the first rows correspond to Laplacian evaluated at red points, and then the second half of rows correspond to Laplacians evaluated at black points. So yes, but it works out nicely in that case. But in general, rows are equations, columns are unknowns. Okay, so I have a system of equations like this. The D1U1 plus FU2. So U1 and U2 are, actually, I'm going to label these differently using red and black. Red, red, and then here I have black. We're only going to have one F, because I can have F transpose down here. Red, black is equal to some right-hand side. I'll call this red and black also. Okay. So now my system of equations breaks down like that. Now, the halves of the solution at the red points and the black points are still coupled together. So at first it seems like we haven't really gained anything until we take into account that dr and dB are diagonal matrices, therefore trivial to invert. So I could do this. I could say that U at the black points is equal to FB minus dB inverse F transpose UR. Okay. Wait. Sorry. That's wrong. I need to have dB inverse on the outside. Okay. So that part's right. So here's what I can do. This system solve is easy. So now I can substitute this expression in here. So I can eliminate UB and solve only for UR. And the only non-trivial system to solve, let's see, if I go ahead and fill that in. So now I have, okay, I need more room. Okay. So now what I have is, if I take this expression for UB and put it in the first set of equations, I have dr UR plus F inverse, sorry, just F, times dB inverse FB minus F dB inverse F transpose UR is equal to little f R. Okay, the only thing that's unknown in here is UR. So I have this equation, dr minus F dB inverse F transpose UR is equal to FR minus F dB inverse FB. So I've trimmed down a system of equations that's n squared by n squared to matrix a quarter of the size. So n over 2 by n over 2 system of equations. Okay, and this type of matrix has a name. It's called the Schur complement. So that comes up a lot solving system equations like this, where you're breaking your domain down into two halves in some way. Okay. Now, this still takes a fair amount of work because F and F transpose are very sparse, but they're not diagonal, so it's still going to take some work. But the point is, it's a lot less work than the original system because you're able to cut out half the unknowns. So once you find UR, you just go back here and solve for UB. Okay, so what we saw here was a kind of a decoupling of the equations, or at least we saw a way that we could decouple them and solve for part of the unknowns independently of the other ones. Now, I had to assume that n was odd. Red-black ordering is kind of separation is possible when n is even. It's just it takes a little more work. Because the problem is, if n is even, let's say this is a red point, that is black, but that's red. I actually made it as a homework problem in my book that have you try it out both ways for odd and even, and figure out what to do to get the same benefit when it's even. But I won't go into that here. Okay. All right. on one hand, I haven't gone through nearly as much of these notes as I wanted to, but I think, well, I just feel the MATLAB details are particularly important because in the end, that's where all the work is done. So what I have in the remainder of the chapter is more on paper stuff. But, well, let's see, we have 23 minutes. Okay. So I'll get through the rest of this section, and then I think we'll call it good. Now, how many of you, because I know that Carly's already done this part of the homework, in homework problem number 2, there's a part dealing with Taylor expansion, and then like a local truncation error. Have any of you gotten that far? Okay. Dang.
Yeah.
What do you have?
Maybe Elf started on 2.
Okay.
But anyway, what's the question?
Oh, I was curious, like where everybody was at in the homework.
Oh, yeah.
Okay, so I guess that's something we're talking about on Wednesday. So, okay. Now, because what happens is when you have any stencil for Laplacian, 1D, 2D, whatever, if you want to get the local truncation error, you do a Taylor expansion and of the exact solution. And you use the fact that the exact solution satisfies the PDE. So in the homework problem, you're Taylor expanding like u of x plus h and u of x minus h. And by substituting in these Taylor expansions, you wind up with uxx. But you take into account that minus uxx is equal to f to get the local truncation error. And you show in the homework that it's order h squared. So, the local truncation error of minus Laplacian of u equal to f. So this is your PDE that you're solving. Or really what you're doing is minus Laplacian of u minus f. So that's the expression you're looking at. You're moving the f to the other side. That is a definition of local truncation error I gave back when I talked about error analysis and lax equivalence theorem and all that good stuff. Because this would be 0 for the PDE, but the local truncation error is equal to your matrix times the exact solution minus your f. And you're only carrying this out for a single point. I mean, the way I've written it, it says local truncation error is a vector. I'm not asking you to produce a whole vector, just what one element looks like. Okay, so in the homework, A is the center difference for minus uxx. So you plug in your exact solution, do your Taylor expansion, simplify, use the fact that minus uxx is f, stuff cancels all over the place. And so I'm going to write down what the local truncation error is. So for 1D, which you'd be crazy to use anything other than the center difference. I'll tell you what you're supposed to get. All right. So I'm concerned about the signs right here. Okay. Oh, the plus. Okay, so if I negate everything, minus. Okay, so AU minus, okay. All right, it's fine. Everything's fine. So what you should get for local truncation error is minus h squared over 12 times uxxxx at some unknown point.
How many
Which-
X's?
4 of them. Because what happens is, when you have a center difference, all the terms of odd order derivatives cancel out. Because you have plus h and minus h. Well, I guess you see something similar to 560 homework. Yeah. At some unknown point, because from your Taylor remainder. Okay. Now, what about 2D 5-point stencil? The expression generalizes in a straightforward way. If we assume equal spacing in x and y, you get minus h squared over 12 again, uxxx plus u y. So you just have the same kind of terms coming from x and y. Now, it's nice that it's order h squared in both cases, but the problem is, now in the homework, in part C, you actually exploit this to get higher order accuracy, because uxxx is the same as minus uxx xx, but minus uxx is equal to f. So you get minus fxx. Well, you can compute that. So in part C of problem 2 in homework, that lets you come up with the leading error term and cancel it out and get 4th order accuracy. Because the next term in the error would be order h to the 4th. The problem is, that's all well and good for 1D, can't do it in 2D. Because this expression cannot be condensed in the same way as this one. So that trick in the homework that's referred to there as deferred correction can't be done. However, there is a way it can be done in 2D. Use a different stencil. It's called a 9-point stencil. Now, 5-point stencil, you're evaluating its Laplacian at a certain point, and then the neighbors, north, south, east, and west. 9-point stencil, you include the corners. So northeast, northwest, southeast, southwest. So all the surrounding points. So 9 points total are involved. And that's a real pain to work out what it is, like all the coefficients, because that's 8 Taylor expansions you got to do. I'm not going to make you do it, don't worry. So it's something you can look up. I think it's in my book. What's nice about the 9-point stencil is the local truncation error, while still having a h squared over 12 factor, looks like this. uxxxx plus 2 uxxyy plus uyyyy, which may not seem that helpful, but this pattern of coefficients, what does it remind you of? Where do you see that?
7 different.
Yes. Where else in an algebra setting?
It's like a no.
Like you think of a polynomial x squared plus 2x plus 1. What can you do with that to simplify it? Or what's nice about it?
It's easily factored.
Factored how?
Squares. X plus 1 squared.
Yeah, the perfect square. What we we have here is the perfect square of an operator applied to U. And based on this, that operator is a sum of two items. It's Laplacian is a sum. So this is actually minus h squared over 12 times the Laplacian of U. Whereas this is not a perfect square, except in the mind of many algebra students who think that a squared plus b squared is equal to like a plus b squared, or God knows what savagery they commit. All right. Well, Laplacian of U is minus f. So this is h squared over 12 Laplacian of f. Again, we can compute that. So with 1D center difference and then a 2D 9-point stencil, we're able to do this trick where we can actually cancel out the leading term in the error and get fourth order accuracy. But as we see, that can only be done with certain finite difference schemes. Okay. Let's see. Okay, not much time left, but so what the rest of this chapter is about is once we choose a stencil for our PDE, and once we have a matrix set up, and it's basically, your MATLAB and you think, oh, it's backslash time. But is backslash really the best thing to do? So there are three kinds of methods that I'll talk about. There's direct methods, which is what backslash does, Gaussian elimination with substitution. Or, in the case of minus the Laplacian, which is a matrix that is symmetric, positive, definite, we can use Gaussian elimination nicely because it means that no pivoting is required. Or we can do what? So Gaussian elimination involves what's called the LU decomposition. There's a different decomposition for symmetric positive definite case. Actually, there's two of them. Oh, that's best for something else. Okay. Okay. You think it still might be in your inventory? Or? Okay, that's okay. Cholesky. Oh. Yeah.
Like 2 or 3 other times.
Yeah. Okay. And then one I didn't really talk about as much, but I brought briefly is LDLT. Okay. All right, so that's one class. Direct methods are those kind of methods. And then there's stationary iterative methods, where it takes the form of a fixed point iteration. Jacobi, Gauss-Seidel, SOR. So these 461 is where I covered those methods. And then there's something I only covered, 610. Krylov subspace methods, conjugate gradient in the positive definite case. And there's like Arnoldi iteration and various mutations of that. So, one could use any of these methods for this kind of a problem. But we're going to talk about like what properties do they have, which ones are best to use in certain situations. And stationary methods in particular lead to a very powerful class of methods for these kind of problems that are called multi-grid methods, which I've not talked about in any class. Well, Haley Dozier worked with those for her dissertation. And actually, so the last couple homework problems you do will deal with multi-grid. Okay, and then if there's any time left in the semester, then because all of this is for time-independent PDEs. What if there's time-dependent, heat equation, wave equation? Well, that PDE becomes a system of ODEs, so we need time-stepping methods for ODEs. Runge-Kutta methods, multi-step methods. So I'll say something about those, although I don't have any homework problems on them. So, but they're important things to know about anyway. Okay. So, alrighty. Well, as far as Wednesday is concerned, see where you're at in the homework, and bring some questions in there. So whatever questions you have right up front ready to go, we'll deal with those things. Then we'll see where we're at time-wise. If there's time permitting, I might continue covering stuff, or it's just a big old homework blitz. So we'll see what happens. Okay. Well, enjoy the video, Carly. Or hope you did. Well, okay, I know you didn't, but whatever.